So first of all, thanks for inviting me. It's great to be here. I would like to follow the previous talk that we just saw and connect the more practical things and the theoretical things. And in general, the more I try to do more practical things since my PhD with Professor Chaire and now Fiat, I see that I need more theoretical tools, and I try to convince you in this talk why. In particular, we'll talk about the connection between robotics. We talk about kind of low-dimensional spaces or three-dimensional spaces in real time, and big data with huge amount of data, huge amount of space, and the relation to the theory of computational geometry. And this work will specifically be an example of work with one of my students, Moat Tukan. A few weeks ago, if you heard my talk, you heard another example. To make sure that I make it in time, I'll first show some cool video that the students prepared. So in general, we are interested in toy robots that just cost a few bucks in Amazon Cloud, in Amazon store. And the main problem with these robots is that they're very unstable. I mean, if you bought one of them in the mall, you know how they're unstable, and they cannot carry too much sensor. So go just use a tiny analog radio camera that sends the video to our laptop, and in a rate of about 60 frames per second, try to stabilize the machine. So you see, this is what the drone actually sees. This is the floor. Try to stabilize, and a human cannot do such things because you need about 100 clicks per second. But the program can, and the challenge is to show that using better theory and algorithm, we can handle Internet of Things, Raspberry Pi, and all these very weak and cheap devices by using software, which is also not expensive. We can usually just download the code, so it's not like buying a hardware from somewhere else. And the main challenge here is to do real-time computations and to solve hard problem in real time using very weak hardware. And the less sensor we have, the more interesting theoretical problems that we found. This is in my university in our department. And in this talk, I will talk about a specific problem. I think we got the idea. I will talk about a specific problem that relate to obstacle and path planning, obstacle observation and path planning, and connect it to problems that looks totally independent in machine learning and big data. So, in general, when we talk about big data, we try to formalize it in theory. We talk about n is the number of points, but it's keep changing. So unlike in common introduction to algorithms, we keep data is unbounded. We keep getting stream of data. The dimension is huge, not just 2 or 3, which is sometimes a problem in computational geometry with many things are exponential in D. We'll see how we can get rid of this. And velocity, so data keep coming either on the cloud or from the robot. So we actually need streaming algorithm, and streaming, I mean only one pass over the data because you cannot get backward, and the memory is only logarithmic in n in the number of points that you see till now. And we also want, either we have a swarm of many robots or drones, or even have or many machines on the cloud. We want to talk about distributed data and still do everything in parallel. So it's not only parallel like in one machine, it's also different machines. So the data is actually distributed. And we don't really want to implement parallel algorithms like in the 80s and 90s, because if you tried, you know how hard it is, especially to debug it. So we just want kind of independent, what's known as embarrassingly parallel algorithm, that every computer just run his algorithm and then they just send the output to each other in some sense. But we don't actually want to implement terrible locks and thread and things like this. It's too complicated for us. And unlike maybe about some kind of online algorithms that assume something about the order of the points or the data that's uniform in some sense, we don't want to assume anything about the data. Maybe the most important points or data will come in 1 minute, in 2 hours from now, and all the important things are there. So if we define n to be the vector that we've seen so far, and we want polylog n memory, If you have n processor, we expect that every time that I get new point, the running time will be only logarithmic in n, the update time. But if I have many machines, say 100 machines, the running time will be faster by 100. So how we can get it? So it turned out that the causal framework, which I work a lot on since my PhD, try to say, let's not try to reinvent computer science to solve these kind of problems. It's very different from what we learn in the university in the first years, because this is not the usual model of offline data that you can just play with on your RAM machine. But instead of just inventing new algorithms for big data, can we use the existing algorithm and still compress the data in some sense? So informally, suppose that we have data D and some algorithm A, and we cannot compute the A of D. We cannot run the algorithm on the data. So we can improve A and try to have better algorithms over time, like we usually do in computer science. But instead, let's try to just compress the data from D to C in a problem-dependent sense that depend on the problem that A try to solve, so that if you run the algorithm on C, which I call core set, it will be fast, and also it will be a good approximation of the result running the algorithm on D. So we need to define what exactly is C. Is this a subset of points? What's a subset? Bits, chairs, other things? And what does this mean, this approximation? And how small is C? Can we actually construct such a C? So, but what unlike many other papers and ideas about just using smart selection of points, so any engineer can think about ideas how to reduce the data, but we really want provable guarantees, both for the running time of computing C and the approximation we see there. We want provable guarantee for any input that D that you'll give me, that I can do good compression, it will be fast, and the approximation will be good. We want provable bounds on everything. And I'll give a simple example, maybe trivial example, just to give you the notion. So suppose that we have n points on the line, and I give you a query tomorrow. I give you this point today and the query tomorrow, and ask you what is the farthest point for my query. So my query, I give you some point here. This is kind of an antenna, and ask who is the farthest customer that will have the lowest connection. Or maybe I put it here. So, but you have millions of points here. But tomorrow when I ask you, in minutes I can tell me who is the farthest point for my query point. So I give you the point today, but query only tomorrow. So do we really need to go over all the millions of points tomorrow to see who is the farthest point? No. Any idea? Okay, it's trivial. So if I give you this Q, who will be the farthest point? It will be this one. If I give you a query here, this will be the other one. So in general, the farthest point can be either this one or this one for every query here. This will be the farthest for every query here. This will be the farthest. So we just need two representative points. And whenever query that I give you, you know who is the farthest. You actually don't need all the points in between. So this is trivial core set, but for example, even for two-dimensional space, the same problem, just the points are now on the map. This trick won't work because you don't have order of the points, but we still have core sets. Just the problem beginning to be more interesting. And in general, we're interested in subset. Usually it will be more complicated. So if we want to formalize things a bit more, so if P is a set, it can be lines, points, bottle of beers, whatever. X is the set of query that we don't know. So P is the size of n. X is usually infinite set of points. All the neural networks in the world, all the deep learning, all the linear regressions, whatever. And cost Px is the fitting cost. If you take a model X and the set P, you need to define a non-negative number that says what is the cost. So you usually want to find X that minimizes this cost. But in the cost definition, we don't have any minimization. We just say that for every given epsilon, which is the error, number between 0 to 1, we want the subset of the points such that for every query that you give me, every model X, the cost of P and X will be approximately the same, like the cost of C of X, up to provable factor of 1 plus minus epsilon. And then every paper we generalize, when we see that we can do it, we generalize the definition of a core set, sometimes weighted set, sometimes not necessarily a subset of the input, and so on. And in general, we use in the recent years more and more techniques for different communities. So it might relate to a PCA and the embedding, strongly related to pack learning, important sampling from statistics. The technique that I'll talk today about will be closely related to epsilon nets and epsilon approximation. If you know about sketch and compressed sensing, it's very related. Compressing graphs and sparsifier, we take many techniques from there. And property testing is a concept with one. So if concept is one hand behind, it's property testing is with two hands because you don't even have time to read all the data. So unlike property testing or sublinear time algorithms, we allowed you to read all the data, but only once, and then you need to choose the points. Other fields just ask you to sample in sublinear time, and you cannot read all the data. So again, during the years from my first paper with Professor Chaire and Professor Fiat in my PhD, I did many courses, usually with some guy from another professor from another community, and we saw how we solve main problem in the field by just making courses for the problem and then running the state of the art on the courses. So it's either the most popular heuristics or exhaustive search, for example, because the course is small, so you can get provable result using exhaustive search. And maybe the most common course set, I think, that people use, it's related to epsilon approximation. We just use naive uniform sampling. So this is related to pack learning. If you give an engineer a lot of data and he get out of memory, he said, let's just take uniform random sample. And if we get a good model for this point, if you cluster the uniform sample, it will probably be good for all our clients or customers. Now, sometimes this makes sense. If you want to know who will be the next president, you just sample a bunch of people and everyone say the same guy, or 99% or 90%. This guy will probably be the next president or woman. So sometimes it makes sense, and we have provable results when uniform sampling actually is a good idea. If you have a lot of points, tomorrow I give you a ball and you want to know how much points this ball will cover up to epsilon fraction of error, we know that epsilon approximation and epsilon nets will solve this. The problem with this approach is that, for example, if we want to do clusterings, then this guy might be very important, but there are very few guys here. And if you just do uniform random sampling, you aren't going to get them. And it might be a problem. Maybe these are the rich guys, maybe they are the bad guys, or the very good guys, or the terrorists, or whatever. Maybe you actually very care about these very strange guys here, and uniform sampling is not such a good idea. So we need to define, in some sense, how a point or a query or an input is important or not for our sampling. And to this end, I want to show maybe the main reason why courses are so popular also now in machine learning conferences, and why it's so easy to implement. Although the proofs are sometimes hundreds of pages, the MATLAB code is just 10 lines of code. And the main reason that I think they're successful is because the reduction from the big data problem to the traditional algorithm that you just run on your laptop with everything in memory. So suppose, I try to explain, it's very easy, simple idea. So suppose that you can compress a set of points to a problem. So we have 2 over epsilon points, we can compress them by half to 1 over epsilon. But we assume that everything on a computer is just a Python or MATLAB code. And it's taking a lot of time, n to the 3. And it's offline, non-parallel, non-streaming, just on my computer. Now I want to solve all the problems that I promised you in the first slides. Parallel, streaming, distributed, streaming data, everything. So there's a magical trick called the merge and reduce tree, actually quite famous for the 17 computer science, that show you how we can do this. And the idea is this. So you have streaming of data. Take the first 2 over epsilon points and compress them to 1 over epsilon. So that's easy because this is just a small set of points. And even if you're slow, it's okay because you just run the algorithm on a few number of points. Then you do this for the next set, and you compress them the problem that if you continue, eventually you have too many compression in memory, and the memory will explode. So instead, we compress we take the union of this compression and compress again, and then take the next set, take the union, compress again, and so on. The problem with this approach is that every time we take a new set, merge with the existing core set, and recompress again, is that the error will eventually explode. Every time that we do compression of a compression, we pay another factor of 1 plus epsilon. It will be 1 plus epsilon to the n after n leaves. So instead, we take the next core set and take the core set of these two. So we're not combining this one with this one. Now we take these two core sets, compress them again, after taking the union, and remove them from memory. So the errors still increase, but only logarithmically because we have kind of a binary tree. Another observation is that we don't have too many core sets in memory because in each level we can have at most one core set. When we have two core sets, we automatically reduce them to one. This is a binary tree, so if you have n points, we just have log n core sets in memory, and we're good. And the other thing is that even if the algorithm is slow and offline, it doesn't matter because the algorithm will always just take two sets, size 2 over epsilon, and reduce to 1 over epsilon. 2 over epsilon, 1 over epsilon, that's all. So the fact that it's offline and just know how to handle a few number of points is not a problem. And it's very easy to implement this framework. Actually, MapReduce and Hadoop actually essentially implement very similar things. So it was very easy to implement this. We have version for Sparks, for Hadoop, for MATLAB, for whatever version you want, whatever system you use for the cloud. We have some code, and in practice we actually see, so this is for real data, on an example core set. So this is the number of points, this is the memory usage, and we see that as the survey predicts, it's really you get the log n factor. The memory is here changed in a strange way like this because this is actually related to the structure of the tree. Every now and then the tree collapses to one root, and then we begin a new tree. So this structure related to how we build the tree. Try to analyze what's going on there. That will be the case. So this was streaming. What about if you have many computers? So we can compute this core set totally independent for each computer, and then collect the results. So again, even if you have no idea how to solve our problem in parallel, finding eigenvectors or God knows what, that's okay because just the compression we do in parallel and then solve the algorithm in one machine. The problem with this approach is that we need to sample all the points and we need to wait and then shuffle the data between the machines. Instead, one of the students, Alton Bagger, suggested that if you have, for example, two machines and you have infinite data, just send the even core sets to one machine, the odd core set to a different machine, and every machine will get a stream. This machine will get a stream of green core sets, this machine will get a stream of pink core sets, and each machine will build this tree that we saw. And in the end, we can send it, or every given moment, you can send it to the main server, only the core set of each tree. So now when we see how core sets are awesome and we can use them for streaming, the main question is how actually we build them. So in this example, you see, for example, when you have an autonomous car, for example, and we collect the image, instead of just deleting the core sets, we actually keep them, so the user can actually zoom in for a specific leaf and see the core set for any specific interval of time. So there are many other applications of this. But in this talk, I will talk about how we compute core sets for convex optimization. And one of the common complaints about core set is that we need a new core set for every problem. So this is good because then I have many papers and not just one. But the problem is taking a lot of time, and we really want a general framework to show, in general, what property do you need for your problem to have a core set for it, like we do with convex optimization, for example. We want a general framework, and so just having more and more papers for more problems. So this is another direction in this step, in the sense that we suggest courses for most of the convex optimization problems, including, for example, logistic regression, and SVD with outliers, and dimension reduction for a subspace under some of the distances, or other not so elegant distances. And the main tool that I will present is a kind of generalization of SVD using corsets for a joint ellipsoid, which is also a classic technique from computational geometry. And then I see the relation to obstacle detection problems, which seems totally with different motivation, but essentially we actually got exactly the same problems there, and I tried to do this connection and show the different application. The most related work related to Clarkson, which is just such concept for a specific problem of L1 regression, but unfortunately it wasn't for every query, just for the optimal solution, so we cannot use this streaming tree that I just showed you. And Dasgupta and Mahoney, Dwinnes, and Harb and Kumar generalized this for any LP regression, not just L1. But here I'll kind of take more generalization to show how it works for general convex function. In the terms of robotics, how to sample space and obstacle detection, this is mainly related to quite popular techniques called RT trees. And it's going to find a heuristic for path planning of the space using sampling. So unlike combinatorics, when you use from computational geometry in the 80s, the piano movies and everything, today in practice, usually people just sample the space and then try to find a path in between. And I show how we can still use very traditional and elegant computational geometry to improve these kind of sampling techniques. So the main tool that I will use is the general theorem that I proved with Langberg, and recently we improved it a bit with Braverman and Lang, which show essentially how we can compute cost for any problem by defining the cost to be a sum of functions. So we assume that the cost is the sum of some function k over the point. You can think about it as a kernel for machine learning. So you have some function k px. P is all the input points, and x is the query. And kpx is just a number. And you want a small weighted sample. And we showed that if you sample the points from the input according to this distribution here, these numbers, then you will go to coset, as I defined before, say 1% approximation for this sum. And the size of a coset is related to something that called the divisive dimension of x. I won't define it, but if you know what is divisive dimension, it's strongly related. Epsilon is the error. And maybe the most important part here, it's multiplied by the sum of sensitivities. So in general, what this point means, how this point is important, it's number at most 1. And you really hope that not all the points are important. So the challenge is to show that for any data you give me, the sum of these sensitivities, this importance, will be small. And the intuition behind this, this formula, I mean, the proof allows, but there is a simple intuition. So we go over all the queries, and we look at the contribution of P to the query related to the sum of everyone, the contribution of everyone. If everyone can be neglected, but you take 99% of the cost, we must take you to the coset. Because if we don't take you for this specific x, we won't know how to approximate this sum. But if for every sum, your contribution can be neglected, say 1 over n, we don't need you. So your contribution is saying, what is the worst case? What is the query that you contribute much more than the other? This defines how much you're important. And surprisingly, it seems that for most machine learning problems, we can bound this sensitivity. Intuitively, it's related to the fact that in machine learning, for example, you have huge amount of data, but the structure is very, you look for a model with a simple structure. So really the sum of sensitivity is related to the number of free parameters, for example, of your model, intuitively. So we have a lot of data, but you look for a simple structure, a few parameters, and that's why the sum is usually small. But the main problem, so this works for any concept in the problem in the world, but the problem is that we don't exactly know how to compute this problem. I mean, technically it's another optimization problem we need to solve for every point. Maybe it's harder than the original problem. So we had a reduction for this problem, but now we need to solve this problem. So, so in the next slide, I try to show how we can bound this for convex function, how this boundary sum of sensitivities for convex function. And using this theorem, we know that we have a coset. So we have a reduction from general coset to sensitivity. Now the question is how to bound sensitivity. That's what we do in the recent papers. And now I'll talk about convex optimization. So intuitively, what does it mean, the equation there? Instead of checking uniform sampling, we define importance for each point or sensitivity. And if, for example, we have a point that is very, very far, we should take it with high probability, but it should only represent itself. So the weight will be 1, but the weight will be very small, but the sensitivity will be very high. But if we take a point from here, so every point will be selected at a very small probability because they are not so important, but because there are many points, we probably choose one. And when we choose this one, we give it a very large weight because it represents many points. So this is intuitively why the weight that you give for every point is 1 over the sensitivity or the probability to choose this point. So let's be more formalized about our case. So I want to minimize or more generally to estimate fx when fx is just the cos p of x. In our case, just the sum of kpx. So k can be any convex function. So f is, or this f should be a convex function. And we want to approximate this sum by only a weighted subset of the point in P. And we want to see how f convex helps us. So the first trick is to look at the query space. So let's take each unit vector x. And for each unit vector x, write the value that we get when you put x on f. So for example, if kpx is just p inner product with p and x squared, so the sum of inner products squared give you fx equal norm px squared when p is a matrix with n rows. Each row is a point in p. And if you get to take some x and compute norm px squared, we get essentially an ellipsoid in the dimensional space. So we take the unit ball, unit sphere, we apply the f on it, and we get an ellipsoid. By just taking for each direction, we just choose the distance to be x multiplied by fx, the value in this direction. And what we get is this ellipsoid. All the ellipsoids contain all the points whose value is less than 1. And the ellipsoid can be represented as by orthogonal matrix. These are the d directions. And diagonal matrix, which are the d values with their radius for each direction. So actually, if f contains millions of points, this is just d by d matrix. And in some sense, we have a concept for this problem in the sense that we don't need all the points in P. All we need to store is this ellipsoid or this matrix dvt, and we know how to answer every query. You give me direction, I just compute dvt x for this direction. I mean, what is the distance for this point to the origin, and then I know what is fx. The problem is that it works extremely well just because we use norm px squared, which is a very specific function, and actually it's also not a subset of the input. And we want the coset to be a subset of the input, for example, because usually in machine learning the input is sparse, and you want to keep it sparsity, so we want subset, not just random projection that might kill the sparsity of the input. So, for example, the linear algebra behind this figure is just that px can be represented by the SVD of p multiplied by x. But then this is orthogonal matrix, so we can remove it. We just get this square matrix, d by d. So it's actually constant with 0 error, but it's not subset of the input. Let's see how it's related to the sensitivity that I mentioned before. So now we actually want subset of the points. So the probability to choose a point is the contribution of p to x divided by the contribution of all the points fx. But kpx is just px squared divided by the matrix norm px squared. And we can just take the square out, and then instead of p, replace it by u, which is the corresponding row in the u dvt matrix, the SVD. And we also replace p by the SVD u dv transpose. And then we essentially can get rid of the u in the last expression because u is orthogonal matrix, has orthogonal columns. So we get only dvtx below, but then we can put it inside, and we get a unit vector here. So u multiplied by unit vector squared is at most the norm of u squared. But now we know, so this is the probability that we should choose a specific point, but proportional to the probability, what is the sum of these sensitivities? Just the sum of ui squared. Why is this small? Because the sum of squared ui is just the sum of squared columns of u. The sum of squared columns of u is just d. So the total sensitivity is d. We just need to simplify something like polynomial in d points divided by epsilon squared according to this probability. This is well known, but it works unfortunately only for square distances because of the beautiful properties of the SVD. Let's try to do it for sum of distance, not sum of square distances. So now kpx is px, inner product, not squared. And the sum is now px1 because we take the sum of inner products between every row in P to x. Now we're in big trouble because it's not ellipsoid at all. Actually, instead of d points here, d extreme points, it might be n to the d number of extreme points, which is actually much larger than our original input, which has only n points. But there is a hope. So this is essentially this set. All the x, such as norm x1, is less than 1. Unlike the case of L2, when we don't get the ellipsoid here, just a very complicated shape. But it's convex. That's the only thing we know. Why? Because f is convex, this function is convex, so it will be a very complicated shape, but convex shape. So now we can use John ellipsoid, which said that every convex body contains an ellipsoid. You see the red one. That actually, if you take this ellipsoid by a factor larger by a factor of d, it will actually contain the object. So in other words, we can approximate fx by some ellipsoid or d by d matrix E, so that fx is just norm 2 of ax, and E can be represented again by orthogonal matrix and diagonal matrix. So this course, since f is convex, we can use this John ellipsoid, and we now define what we call the FSVD of P. So dvt is the ellipsoid. Now we can just find the u such that P will be equal u dvt. The problem is that unlike in the previous case, u can be almost any matrix, not necessarily orthogonal matrix, but I still keep the naming so it will look like SVD. And this is still ellipsoid. But we're still only in the beginning because there are two problems. First of all, unlike the L2 case, it's only the approximation. And I promise you 1 plus epsilon approximation. And the second thing is not subset of the input. So this is an approximation to fx for any x, but we want subset of the input points behind fx. But it's a good start. So we know the sum at least, we know how to approximate it up to a factor of d. How now we can use sensitivity with this to take a subset of points. So we want to bound this value, kpx over fx. Let's try to do the same trick that we did before. So this is just px divided by the norm of px, norm 1 of the matrix P multiplied by x. Again, we can replace P by du dvt. Now it's not a SVD. It's the SVD for the new function that we found using the ellipsoid. So dvt is the ellipsoid, and u is the matrix that we need to construct to get u dvt equal P. But now we cannot just remove u because it's not into orthogonal, but still, because this is just the denominator is just the fx, we know that fx is approximately dvt, so we can still remove u. So we pay a factor of d in between, but we can get rid of the u, and then again we have u multiplied by a unit vector, and now it's less than the norm u1, because we don't have the squared here. So we can still use it to a good approximation for the sensitivity. And the sum of sensitivity will not be 1, maybe this square, maybe this 3, but not too much. But I'm not sure how to bind the sum of this sensitivity now, the sum of u. So to do this, we try to generalize this technique for any, and also we use the fact that actually we have inner product above, and we actually want to say that it works for almost any convex function, not just some nice inner product. So what we'll do, we'll assume that we use two assumptions that we can get rid of them in some sense using level sets later. But in principle, we assume that kpx is just g multiplied by a function of px. And also that we can multiply x by some vector and get the same k. So we can multiply by a and then get the same result as we just multiply x by a. And by this similarity, I mean up to a factor of poly d. So we pay for, in the total sensitivity, we'll pay for it, but that's all. So let's see how it helps us. So the main result is that the sensitivity of every point, which is this value on the left, is at most this value on the right, which is independent of x. So you can simply compute it for every point if you know what is ellipsoid, E. And the total sensitivity is only d to some constant, independent of the number n of points. So this is the primary result in which for every convex function that satisfies what I wrote below in the previous slide. And now we have only two hairy slides, because we must. And then I'll try to return back to the robot and see how it's related to them. So the idea that we use is just that the denominator fx is just norm ex by the joint ellipsoid. And now we can put the ax inside by the property of k. And now we define y to be ax divided by norm ax. So we get this kp, this value is just e minus 1y. And p is the same as u multiplied by ellipsoid by the definition of p equal u dvt. The next equation is just g equal inner product of uy by the definition of g and k. Now g is monotonics and y is unit vector, so uy is less than norm 2 of y, which is less than norm 1 of u. And when you have the norm of u1, you can now sum over all the standard vectors. So ei is just a vector with 1 in the i's coordinate and 0 in all the others. And using Jensen inequality, we can actually take the sum outside. And then we get rid of the x, return back to k by definition of g to get this value. And ue, again, is by definition the point p. And this is the sum of sensitivity. This is the sum of sensitivity essentially for a single point. But why this sum is small? So to bound the total sensitivity, we take all this sensitivity and sum them over all the points to make sure that not all the points are important. So let's bound it. So the main trick is that we have sum of all the points and then sum of all the dimension. So we just switch these two sums and get this value to the right. And now this value is just the sum I1 of d on f, because the sum of all the k's is just f for the specific query, a minus 1 ei. And then we can just replace f by the ellipsoid because we know that fx is just norm ex, and then the 2e cancel, and we get just the sum of standard vector, which is d. So again, it's a bit complicated, but just simple in algebra in the end. I mean, there's not too much hard theorems inside, but still we got wonderful results. I won't show you all the experimental results on the machine learning. But I want to talk now about the relation to the ellipsoid. How much time do I have? Great. So the problem that I didn't mention till now is how we get this ellipsoid. So okay, f is convex, but it's living in a high-dimensional space. It has many vertices. We know that there exists some ellipsoid, joint ellipsoid, but the question is how to compute it. So we have this set. All the points at the fx less than 1. We have f, but we don't know how this strange object looks like. It's a huge object n to the d vertices. So we actually want to compute it. So the trick is just to use Oracle membership. So if I give you a specific x, or a specific point in space, you can tell me whether it's inside the object or not. So you don't know how the object looks like, how this is convex shape, but you know how to answer Oracle membership queries, which means that if I give you a point in space, you can tell me if it's inside or outside. So actually we want algorithm that will solve it using Oracle membership. We found some algorithm, but extremely inefficient. We want to implement it to run it in practice. And then we found out this is actually exactly the robotic problem that another group works on, which is related to the obstacle detection and avoidance. So if you know the game Battleships, so the idea is that the opponents put some battleships, which are just some shapes like this, and you need to guess, to just hit with like Oracle membership, whether you have something here or here, and the opponent will tell you yes or no, and you need to decide where all the ships, all the battleships of the opponents are. But you can always ask, do you have a battleship here or here? You just hit, and you get the answer yes or no. But this is essentially the problem that we get in robotics in two scenarios. So the obvious scenario is you have a drone that sees a video in the forest and try to go to the other side, then you don't have time to read all the high definition video. You can just need to sample a few points, decide where are the trees, and then continue. So again, you have obstacles, which are the trees in this case, you have the image, and the question is which point to samples in real time to decide where to go and where are the obstacles. But actually, even we talk about higher dimensional spaces, like if you want to park a car, or if you have arms, then or just you have the piano mover problem that you want to take a piano out of the room. So the problem in the 3D space, but the control, the parameters for the control are actually in higher dimensional space. You cannot move from every point to every point when you park the car. You cannot just park it in parallel. So you have high dimensional space. You have no idea how it looks. You don't know how actually what movement you need to take the piano out of the room. But you can answer the question, is this configuration is feasible? Can we be here? Like exactly in this game. With a point, you can get yes, no questions. So essentially, we have the same point. The problem to talk about here, that we have convex shape, we just have Oracle membership, we want to approximate it, is exactly the problem that we have for obstacles for the robots, that either go in the dark, or very fast in read image, or just using high-dimensional control space. So that was the other challenge. So we try to use the existing algorithms for sampling space, and the problem that they use heuristics, and they just prove that in the end, if you sample enough sample, infinite number of samples, it will converge to what you want. But they did many strange things in general. Like for example, if the object is some ball inside the box, you see that they have three queries here, here, and here, and the answer is yes for everyone. So this point is in the ball, this point is in the ball, and this point is the ball, but you don't know the ball. And then we see that the next query is just inside the triangle. But we know that if this is a convex shape, and this answer was yes for all of them, you don't need to query anything in between. Everything here is inside the ball. So the current algorithm just ignore the property that we know that objects are usually nice and smooth or convex or can be partitioned to many convex shapes. And we want actually algorithms that will find the best path and understand what is the map exploration, but with minimum number of queries. So it's like the best battleship strategy. What is the minimum number of queries that I need to make to get the best good approximation, say epsilon approximation for each of these obstacles and shapes? So when you run our algorithms, I won't have time to talk about this. It's another presentation, but in general, when you run it, you see that again the RT algorithm keeps sampling points around. Where our algorithm, when you find an object, you keep improving the accuracy of the object, and we get significantly better results, but also provable bounds on the number of queries you need to take related to the approximation that you want to get. The intuition of the algorithm is this. First of all, when you have no idea what's going on, all you can do is just take random sampling of the space. But we really want, instead of just random, we want to make it smart, so we check a grid and take just one point and then find a grid until finally we hit an object. When we hit an object, we want kind of concept for a joint ellipsoid problem, which essentially means try to go out from this object and see what are the boundaries using some ellipsoid algorithms until we get some good view approximation of the object. And then we try to just do epsilon grid on this approximation to get a final approximation and get the exact bounds of the object up to some epsilon. So, so again, you have all the code in our website, and we hope to send you also some videos soon. So you can just Google my name with the Robotics Lab and download both code systems and send us email if you need support. I will mention some open problems that we work on these days. So first of all, we want the concept for deep learning, which is very popular these days. Now the idea is either to make deep learning faster, so instead of 2 weeks of training, you will have 2 minutes of training. But the real goal is just to get rid of deep learning, as we show that we can run, for example, a photo vector machine, which are models that we understand much better, on the concept for deep learning. So we don't really need deep learning, because sometimes people say that we just run deep learning because we don't know how to run algorithms on big data, but using concept you can. So maybe deep learning is not the only solution for handling big data, and we can try to do better using algorithms that we actually understand much better and concept. There are millions of problems in machine learning that still don't have concept, but fortunately we have concept in machine learning conferences every year, more and more. And as my friend said, it's kind of make computational geometry great again, in the sense that more people outside the community use it. There are other orthogonal directions that relate to encryption and privacy, differential privacy, and we found surprising connection between compression and encryption and privacy. For example, in homomorphic encryption, we try to run algorithm on encrypted data, and the problem with this field is that it takes huge amount of time to just multiply two numbers between 1 and 10, take half an hour if they are encrypted. So we show how concept can help this. It will be on the archive, I hope, next week. And more general, we hope to get more code and libraries. So even if you can't read, or engineers that cannot read all the long papers and proof, you can still run the code, evaluate it, and maybe then convince them to actually read the papers and learn the theory behind it. And I think one of the most other important problems related to sensor fusion. So we have experts in image processing, in GPS, in speech recognition, text mining, but for real-world problem, we usually want everything together. So we want people that will solve, for example, to understand what I'm saying, you need both my image and my lips and also my voice. So we want to do more sensor fusion, and I have courses and algorithms that combine many sensors, and especially it's true for the drones and the robots, for example, that have so many cool sensors, 2D cameras, 3D cameras, the ultrasonic sensor for the sound, and so on. So we need more algorithm for this kind of sensor, not specific sensors. I think that's all. Thank you so much.